We're looking at ray diagrams in human eyesight today. The idea is to take an application of our understanding of lenses to understand why there are different lenses for near and farsightedness. This is something you can learn as a technique to think your way to the answer rather than memorizing it. So I want to look at two of the conditions required to see an object and where textbooks are frequently wrong. So on these 2 pages, we're going to look at the top one first, which I have down here for us to look at. So if we have an object out here, well beyond 2 focal lengths away, and you do the ray diagram, you will see an image is located at A. If we have this retina here, and we want to see that image, this could be your retina in your eye, it could be the camera sensor, it could even be the projection screen. The question is, do we want to put the capturing sensor where the image is or where the focus is? Now think about it. If this is where the image is forming at A, that's where you'd want the sensor, because all the light from the arrow tip is reformed right here at A. If you put it at B, you're going to have 3 arrowheads here. This ray is up here, this ray is lower, and the third ray is down at the bottom, but they all came from the same starting point. That's a blur. It's not an image. You put the retina here. So if we were to write this down, the image is at A, not the focus. Put retina here. Okay, that seems pretty straightforward. The data projector in our classroom is going in reverse. So when you're looking at notes on the screen, the data projector is projecting a tiny upside down version, and the projection screen is here, not there. It would not get an image. The image occurs where all the light reconverges. Nowhere else in here has the light come back together yet. Only at this point here, and in the reverse case over here. That's where the retina goes. Seems fairly obvious, but that's not what the textbooks do. This is frequently what the textbooks show. They will go ahead and draw an eyeball. So the only thing missing here is if I put an eyeball in like that. And they'll draw the human eyeball, and they will show the light focusing on the retina. And that is really wrong. There is no image at the focus. And you're not focusing on parallel rays. So they lead you to suspect that you've got to have this bright focus right on the retina. Well, this means the image of the sun has been shrunk down to a tiny point. That's not an image, it's a dot of light. And I took you outside and you put your hand at the focus of a mirror. You don't get an image there. What's going to happen here all you're going to do is burn a hole in your retina. Staring away at an infinitely far away object, the light will come together at the focus, and that is not an image, that's just an intensely bright spot of light. And for some reason, diagrams like this persist in your textbooks and elsewhere. They really should be showing this kind of diagram here. They should be showing the human eye drawn in the diagram like this, and the retina is not sitting at the focus, but the retina should be back here. Instead, they keep producing this diagram repetitively. This is a burning of material. This is not creating an image. All right, so let's move on briefly. Now that we've seen this, let's take a look at how we can determine what our eye sees and how we fix it. We have 3 possible lens shapes in our eye: a relaxed lens, a stretched lens, and a very spherical shape. This is done with the little muscles that pull on your pupil, or the lens behind your pupil. When we get a bigger curvature, right, a closer to spherical thing, the focal length shortens. When the lens is nearly straight, the focal length is long. How could you remember that? If you look at any glass bead, there's a huge distortion of light. So there's a tremendous bending of light going through. And the ultimate stretched lens would be a flat sheet of glass. When you look out a window, do you see any magnification presence in a flat sheet of glass? No. So a flat sheet of glass would effectively have an infinite focal length. So you can think your way to which one of these bends the light the most. And then we're going to try to decide which lens goes with each form of eyesight here. So here are our three lenses. And there's a moment here where there's learned helplessness. Let's suppose you forgot the ray diagrams, how to do them. But there's a complete one right here showing a person, here's their eye, lens, staring at an object reasonably far away from the lens. And here's where the image landed. What happens if this object moves away from the lens? Well, we do the ray tracing now. In through the center, out through the center, just like this one. We go in straight, and then you go through the focus, like that. And finally, the opposite, in through the focus, out, parallel. Okay? Just like you see down below here. And look at that. The rays came together right there. So we have a smaller inverted image, right? But it's no longer on the retina. It's landed in front of it. The light was bending too fast, so the image formed here, and by the time the light reaches the retina, it's spreading out. So the rays came together too quickly to focus. Now what about down here? Let's try it again. Without that, I gotta go back to my line. In we go. Okay. In we go. And the focus is not very clean because this happens on large diagrams. It's not your fault, but clearly the image is forming behind the retina. So in this one, the rays were being converged too quickly. And on this one, the rays didn't come together fast enough. So if you think about it, we need to relax the bending of these rays. This lens needs to lessen its focal length so it isn't so aggressive at bringing the rays together. And this lens here is not being aggressive enough. It's not bringing the rays together quick enough for the person to get a clean focus. So what do we do with that? Well, let's look here. This lens will not bend the rays as much. This lens will bend the rays more severely, and this is the normal one. So I think it's pretty obvious that this lens goes with this ray diagram. The question is, do we want a gentle lens curvature or an aggressive lens curvature in each of these two cases? Well, think about it. This curvature is not aggressive enough. So we're going to want to put in there a fairly aggressive lens with a nice short focal length to force the rays to come together quicker. And this one, the regular shape lens, isn't working. It's bending it too quick. So in this one, we would want a nice gentle lens shape to allow these to relax, where the ordinary shape is here. So you can think your way to the answer, and then we'll discuss why we call it near and farsightedness next.